All right, we're going to look at average atomic mass, which is essentially a way of accounting for different isotopes of the same element. Okay, so to distinguish between one isotope and another, we have this thing called the mass number. That is the number of protons plus neutrons that are together in the nucleus. We usually use that to kind of tag an isotope so we know which version of the element it is, either lighter or heavier. Okay, but when we do stuff in the future, we want to know what is the actual mass of something, not just relative. It's heavier, it's lighter, something like that. We can't use grams for mass of atoms because the gram is way too large. I mean, to us, the gram is small, but in terms of atoms, it's huge. It's way too big. So instead, we needed a new unit of mass that is for atoms specifically. So we came up with the atomic mass unit, AMU. Very clever name. Okay, the mass of a proton or a neutron is about 1 AMU, and the electron is very, very light in comparison even to that. So that doesn't factor much into the mass of an atom. So the atom's mass is about the same as the mass number. If we have 15 protons plus neutrons, and each one is about 1 atomic mass unit, the mass of that atom is going to be roughly 15 atomic mass units, 15 AMU. Okay, not exactly, but it's going to be close. So for instance, beryllium-9 has an atomic mass of 9.012 AMU. But beryllium's example is a little bit easier because there's really only one isotope of beryllium out there. We don't really find other versions like beryllium-10 or beryllium-11 or beryllium-8. So whenever I'm dealing with beryllium, I can say, well, the only version I've got is beryllium-9. It has an atomic mass of 9.012. So that's it. But a lot of elements have different isotopes that have different masses. So I can't just say carbon has a mass of this or phosphorus has a mass of that because there are different versions out there. And which one do I pick? Or how do I accommodate for all those different versions? Well, the answer comes from this. So this is kind of an example of carbon, where I've got mostly carbon-12 atoms, but I've got one bigger carbon-14 atom here in the middle. Well, I could say, well, I mean, most of it is carbon-12, so maybe I'll just say it has the mass of carbon-12. But that's not really true because I've got some carbon-14 here and there that's going to make it weigh a little bit more than that. So I can't just settle for one isotope that is kind of the more popular, the more common option. I also can't just shoot for the middle and say, well, I've got 12, I've got 14. Maybe I just say it's carbon-13, and I just get the mass of carbon-13. They're not the same. What we call abundance. One is more abundant than the other. The carbon-12 is way more common than the carbon-14. So I can't just kind of meet in the middle and say, oh, that's close enough, because it's not true. Most of my mass here is from carbon-12, and only a little bit is from carbon-14. It's going to nudge it a little bit up higher from carbon-12. So in this whole sample of carbon, I need one number to be able to describe the mass of carbon. What we get to is something called the average atomic mass, but it's not a regular kind of average where we just take, two masses of two different isotopes, add them together, and then divide by 2. Or if we do it for 3, add 3 together and divide by 3. Instead, we do what's called a weighted average that uses that abundance, how abundant or common or popular they are, okay, how often they show up, tells us how much they should play a part in that average. Kind of like if you have a grade where like 15% is homework, 25% is quizzes, 30 is tests, or something like that. Okay, same kind of idea. So this weighted average is what we use for the average atomic mass, and mathematically it works something like this. We take the mass of each isotope that we're dealing with multiplied by its percentage. That is the percent abundance, how frequently it shows up. We do that for every single isotope. So if we have 2 isotopes, we do this twice. If we have 3 isotopes, we do it 3 times. 4 isotopes, we do it 4 times, and on and on and on. Most of our examples are going to be, 2 to 4 isotopes, because otherwise it's just making the problem longer and longer. Okay? If we go and add up each contribution of each isotope, we wind up with a weighted average, what we call the average atomic mass. Now, something you have to be careful of is percentages kind of hide the true nature of a number. So I can't just multiply by 50% and hope for something to go right. Multiplying by 50 is going to make my number way bigger. What that 50% means is actually 0.5. It's 1/2. So I want to multiply by 0.5, not the actual percentage as it is. So grab a pen here. Make sure on all your percentages to move your decimal point 2 spots to the left. Otherwise, we're multiplying by the wrong number. We want the true value of the percentage. Okay, so each isotope is going to have its mass multiplied by each percent as a decimal. Change to the decimal form. Now, some problems are also going to get a little bit trickier in that we end up looking for, let me change colors here, we end up looking for one of these masses instead of just plugging them in. Usually we just get a whole bunch of data and we're able to plug it in. So, if we're missing this piece, how are we supposed to calculate this here, or vice versa? So problems can get a little bit trickier, but this is kind of the base formula that we're going for. So when we go and actually calculate the average atomic mass, we might get something like this. Mass times abundance, mass times abundance, mass times abundance for each of these 3 isotopes, in this case carbon-12, carbon-13, carbon-14. And then we add up each of those contributions and get an average atomic mass in AMU that describes that element as a whole, with all the different isotopes depending on how abundant they show up. Now, this is actually something you can find on the periodic table. If you go and look at the block for carbon, down kind of on the bottom, there's usually a decimal number there. That's like 12.01 or something like that, which is pretty darn close to what we calculated here. Okay, so the periodic table actually shows you the average atomic mass, meaning you can really check your answers when you're doing these problems. If you go and calculate the average atomic mass for copper, you better be getting something close to 63.55, or else something went wrong in your math. Okay, it might not be exact, your rounding might be a little bit different or something like that, but it's going to be pretty darn close. Now, I mentioned also that some problems can get a little harder, where we end up having something like where, oh, got my equation up there now. We end up having something where I'm looking for the mass of, the mass of like this isotope here. Okay, and I also don't have its percentage. Okay, well, without those, I can't calculate the average atomic mass, which means I'm missing like 3 bits of information. Algebra is good for finding one missing piece of information, not 3. So if my goal is to find this mass of this isotope here, how many AMU that one specific version of this element is, I'm going to need to get crafty. So the first trick is to look at your percentages. Your percentages should add up to 100%, like these do. 98.93 plus 106 plus 0.01 should give me 100%. Okay, so if I know this percentage and this percentage, and I subtract those out of 100%, whatever's left should be this percentage here. So I can find that. Okay, so that's good. I'm not stuck with having to figure that one out. But I'm still missing this average atomic mass here. Well, if we had all the information, it should turn out to be the thing that's on the periodic table. So maybe in this case, I can just kind of steal it. I just go to find the element on the periodic table. I look up its average atomic mass, that little decimal number in the bottom, and I just plug it in. At that point, then, the only number I'm missing is this mass right here. Now, it takes a little math magic to get that. It's not an easy algebra problem to work out, but it can be done. My advice is to go through and multiply these guys first. Let me switch back to N. Do these first. Multiply. Multiply. Do that for as many isotopes as you need to. Okay? Add those together. Condense basically and clean up whatever you can. And then get it off of this side and subtract it out of the average atomic mass. So you end up with a much smaller number over here, and these guys go away. So clean up as much as you can first. Then, once you've got all that taken care of, we can divide away this percent as a decimal from both sides and be left with just the mass here. Now, you can also check your answer with this as well. Since the mass of a specific isotope should be very close to its mass number, like carbon 12 has a mass of about 12, carbon 13 has a mass of about 13, carbon 14 has a mass of about 14. You can use this to estimate what your answer should be for the mass of that specific isotope. So if I want to know the mass of a specific isotope of nickel, say I want to know what nickel 59's mass is going to be in AMU. Well, it should be close to 59. Maybe it's a little bit lower, maybe it's a little bit higher, but it should be pretty darn close to that. So if you get something vastly different, you might want to check your math.